And also his work with the longtime collaborator Fernanda Viegas currently focuses on making AI technology broadly accessible and reflective of human values. So Martin has done a lot of great work very broadly and in the general space, and also his work has also created end-user visualizations for products such as Search, YouTube, and Google Analytics. And I'm particularly excited for this guest lecture. And Martin has done a lot of great work in the space, and he's going to tell us more about these models within models, how LLMs represent the world. So with that, thanks, Martin, for joining us.
Great. I'm delighted to be here. Thank you for that introduction. And let's see, let's begin. So back in 1950, Alan Turing asked this famous question, can machines think? Today, we're asking slightly different questions, but in many ways, it's kind of getting at something similar. People are wondering, do neural nets understand their input? In some sense, I'm putting quotes around understand, or do they operate via a set of haphazard statistics? And these are incredibly interesting questions, I think, but they're also can be very frustratingly vague. And in fact, trying to make them specific enough that we can actually apply, so the scientific method to them is very hard. And so I want to talk about one way of approaching this type of question. I don't think we'll answer whether machines can think or not, but we can answer something that is still very interesting. So here's another way of looking at this general idea of understanding. We can think about two ways that a neural net could be operating. These images, thank you, ChatGPT, for helping me out with them, show two possible ways things could work. We could imagine, on the one hand, maybe an AI system takes in its input and it forms a mental model of some sort, which it uses to get at the output. The other way of looking at things is that it is regurgitating. For some reason, people love to use vomiting metaphors in this context. It is regurgitating its training data. There's no mental model of any sort, nothing like that. It's just a set of statistics. So this idea of looking for models versus just pure memorization gets us a little bit closer to something we could study. Let's try to make it even more specific. What do we mean by this sort of internal model? So the idea is that if you have some computation that the system is doing, so for example, maybe it sees an image of a rose and it creates a caption like a sweet smelling rose, we can think of that as a very complicated function that it's applying. And to say that there's a model, one way of looking at it is to say that that function factors in a very sort of predictable way, in the sense that it factors into two functions. First, it takes in the input and it creates some representation of that input, which is recognizable to us as a simple and interpretable representation of the world. And then it operates on that representation to get the output. So without getting into too much more rigor, I'm going to say that this is our working definition in this presentation of what it means to have an internal model of the world. Okay, so this gives us a general idea of what's going on. Let's think about how we could study that. I want to talk about a couple of pieces of research that came from our lab that can help us illuminate how this works. Okay, so before we do that, I mean, it's worth saying, like, why should we even care about this? And like, one thing is I personally find it really, really interesting. And let's not forget that the intrinsic intellectual joy of exploration is something important. But there are these other considerations, which also mean a lot to me. When you are working with AI models, one of the big questions is, should I even trust them? What are they doing? It can feel like this horrible black box in many ways. You also could ask about reliability and safety. If they're just applying a set of heuristics, you really have no guarantees about what they'll do next. If you could identify some internal model that they're using, that provides the kind of foothold you need to start climbing up a ladder towards robustness. Maybe you can start, analyzing exactly what happens to that model to understand, what sort of guarantees you could give. And then I would add that I think there are even ethical considerations that come into play as well. For example, if you think about the generative AI system that I use to create those images, there's a very active debate about to what degree is that, sort of creating something original versus simply ripping off artists. And in many ways, I think the answer to that question combines some questions of values of what we're going to say matters as people, but there are also these technical questions about, is it generalizing in some way that is going beyond the original training data? And all of these things, to answer these questions and all of these issues really sort of, require knowing something about what it's doing internally. Okay, so the big question, though, is that it's really hard to figure this out. And if you look at a large language model, they're enormously complex. And if you're looking for a world model, that's also really complex. So the world is really hard. And, how do you look for a model in the internals of, one complicated thing inside of another complicated thing? So one technique we can do, one strategy, is to simplify greatly. And what we're going to do is study a medium language model operating in a small world. And it's going to be architecturally the same as a language model, but this will give us a chance to understand what are the capabilities and limits of its computation. Okay, so this comes from, and it's a paper published in iClear. And what we're going to do is we're going to take the world of a simple game. It's a game called Othello. It looks visually like a small version of Go, but the rules are different. Some of you may have played it. It's like, for some reason, I played it in elementary school all the time. And the idea is that two players are at an 8x8 grid. One is putting down little white chips. The other is putting down little black chips. And the goal is by the end of the game, you want more chips of your color. And the way the game works, and I'm going to just walk you through some sample moves just so you understand what we're dealing with here, is at the very beginning, there's always the same sort of start of the game. You have two black chips and two white chips. Unlike chess, black always goes first. And when black can put a chip anywhere that will sort of surround, either vertically or horizontally, white chips. So here, black in the very first move has played at E3. And so they put down a black chip, and then that surrounds that white chip that used to be at E4, flips it to black. And so now black is, for the moment, in the lead. And then in the next move, you see white has surrounded this black piece in this horizontal row and has flipped that to white. So now has drawn even again. Again, the idea here is that the moves are relatively simple. One important thing is the only legal moves are those that will surround a piece of your opponent. So for example, there's no way that black could move, or white at this point, could move at square A1. That would just be flatly illegal. Okay, so now you basically know the game. And you can see that to define moves, it's just a sequence of which square each player moved at. And the legality is a little bit tricky to figure out, but it's not hard. Kids learn it. And there's sort of a funny, the board itself is like a nonlinear function of the moves. Okay, so that leads us to this question. Can a language model learn to play Othello? It's a little weird because it's not a language, but after all, language models like GPT, and we started out with something close to GPT-2, they're after all sequence models above all else, and we can think about a game of Othello as essentially a sequence of moves. So an example task that this system would be trained on is it's given these moves that you see as letters and numbers in orange that are just describing grid squares. This would be part of the game, and it's supposed to guess what square comes next. Now, again, I want to emphasize here, there's no a priori knowledge that this is a game. There's no rules built in. This is not, AlphaGo. It doesn't know anything about the board. There's no inductive bias that there's a board, in terms of a convnet or something. It's just sequences of tokens, and it's just a standard transformer. And just to emphasize, the reason that we're doing this is because we're making this analogy. We're saying the moves are something like a very, very simple language. Like a linguist would probably hate that I'm calling it a language, but it's a structured sequence. And the board state corresponds to the world. in the sense that the board state is not at all explicit in anything happening here. Instead, it is sort of part of the world or the environment that is generating the moves and that the moves have to do with. Okay, so what happens when you actually try to train a GPT variant to play Othello? Well, so that is our first question. And in fact, the answer is it actually turns out to play legal moves really well. And we did this in a couple of ways. So one is that we had what we called the championship data set. This came from real games played by skilled humans. And then we also had a larger random data set, which basically we generated and came from random legal games. So they were legal, but they weren't necessarily like good moves. They were just legal moves. And in both cases, the system actually learned to play with legal moves with a fairly low error rate, doing especially well with random one, likely because it's larger. Okay, so I should also say that like this is not hugely surprising. We sort of knew that this was going to happen because if you look, for example, at things like GPT-3 or GPT-4, they already can play a little bit of chess, not always perfectly, but we've seen these language models pick up this type of gameplay. So we went into this kind of deliberately guessing that this part of it would work. But what we were really after was question 2. How does it do this? Because the legality, as you saw, is based on the board position, but all it has as input is the moves. Okay, so it makes you wonder, is there a representation of the board that it is building? And in fact, it turns out that probing suggests that indeed the predictions factor through a representation of the board. And I'm going to go over a little bit of how this works. I know that in some previous classes you've talked about probing, but just to kind of set terminology, because this will come up in the next example as well, I think it's worth talking through. So the idea for probing for representations, again, this is an old idea, it goes back, at least 8 years, is that the setup is that you have a neural network with multiple layers. It starts out with an input. Each of these sort of orange rectangles represents a layer, and you can think about the activations in that layer as representing a vector in a high-dimensional space. And during inference, you put in the input and you get a series of activations. And then the question is let's have a concept in mind, and we're curious if the system is representing it in some way. So what we do is we say, we're going to see if we can train a simple classifier function on these internal representations to see if it can actually detect the presence or absence of that concept. Okay, so for example, this is something that people play with like in a vision network, and you might say, oh, does the vision network know about eyes at layer 3? You would train a classifier basically to look at those internal representations and give you, say, a positive value if the eye is present or negative if the eye is absent. And essential to this is that it has to be a relatively simple classifier function, because in fact, if there's a lot of information in one of these middle layers, some very complicated neural network could probably extract it. And it doesn't really tell you that there's a representation. It needs to be simple for this to be meaningful. Okay, so then when we do, so going back to Othello GPT, we can say, for each square on the board, could we train a simple classifier to figure out whether that square is white, black, or empty, and train it on the internal activations? And it turns out that absolutely, it turns out you can. And you get so what you see here is the table of the error rates for trained classifiers. Each column corresponds to one of the layers in the network. And then each row tells you one of 3 possible neural networks that we looked at. So as a baseline, we looked at a randomized network where we just didn't train it at all. And you can actually see that the error rates are not terrible, actually, for a randomized network, which is interesting. That tells you that a certain amount of information just propagates through. And honestly, the baseline, for example, for much of the game, most squares are empty. So it's not that hard to get a decent score on whether, if you had to guess whether something is black, white, or empty. Guessing empty is a pretty good guess. So the randomized row gives you a baseline. For the championship games, which is a relatively small data set, you can see we can get much better than randomized. So it's clearly getting at something in there. And for the network trained on synthetic games, you can see that for like the later layers, you actually get an extremely low error rate. So what this tells us is that there is something like a relatively strong representation of the board state at any given moment. Okay, so there is one last box that we need to check that's really important, which is that it's possible, it's conceivable, the network is creating this representation, but not really using it. And this has been pointed out by a bunch of people, but there's a great article by Belenkoff from 2021 that lays this out in great detail. So how can we test this? Well, we can try to intervene. We could actually go in and change the activations during inference. So we perform inference, say, up to a certain point. We then go in and forcibly change the activations so it would flip our classifier, and then we see if its predictions actually change as if we'd flipped that square on the board. And it turns out if we do this, it does exactly what you would kind of hope, is that we can actually predictably change its predictions. If we flip a square so that our classifier moves from thinking it's black to white, suddenly the legal moves will correspond to white rather than black. So we believe that this is a real representation. Okay, so basically, to sum up, does this system actually learn a representation of the board and use it? Yes, we can find it by a sort of probing classifier method, and we can change the representation in a very predictable way, so that in a way that is sort of predictable and interpretable on its own predictions. Okay, so this is actually kind of a nice result because it tells us that there is something like a world model in this very, very toy example. Now, I want to talk about some nuances, which I think are sort of worth getting into because it's good food for thought. So one is to ask, what exactly is being represented? What have we found? So the original work on this that came out of our lab is we had a relatively simple classifier, but it wasn't linear. It was basically a two-layer neural network. And when we tried to get a linear classifier that could tell the difference between black squares and white squares, every time we tried that, it failed. So we moved to this two-layer network. It succeeded. We thought, okay, good. The main thing is we've shown that there is a representation. Then another researcher, Neil Nanda, actually came up with a very clever discovery where he looked and said, what if in your linear classifier, you weren't trying to figure out whether a square was black or white, but you were trying to figure out whether a square corresponded to my color or the opponent's color, where that flipped every move. And it turns out that there's a linear representation of that. So it's kind of a fascinating example of when we look for world models, in a sense, there's a question of what we're looking for. Like if we try to find something that's like obvious to a human, like black versus white, we might end up having something a little bit more complicated. And the fact that there's a much simpler representation of my color, your color, maybe tells us something about how this neural network is operating. And in fact, the more you think about it, the more you think actually the my color versus your color is a really intuitive way for the thing to be calculating, because that is really what matters for the next prediction. Once it's got that representation, it can use the exact same sort of circuits, presumably, in order to predict the next move. Okay. There's another nuance that I do think is important because as much as I'm excited about finding world models inside of neural networks, I also don't want to overstate what's happening. I think it's important to be grounded in reality. And with Neil and Andrew Lee, we did some work where we're sort of looking at exactly how much this board state was used. So as I mentioned, you can sort of intervene, and generally interventions work pretty well, that it will change the predictions in a way that corresponds to the intervention. But it doesn't work perfectly. And weirdly enough, the errors, the times that these interventions don't seem to work as well, there's a pattern to them, which is that right at the end of the game, the interventions dramatically work much, much less well. We do not know exactly why this is. It's actually somewhat mysterious. And our guess is that it's a couple of factors. So one thing is that by the very end of the game, it's really easy to predict what the legal moves are. So for instance, when there's just one empty square left, basically almost always it's just a legal move to that square. So you can imagine that simple heuristics that don't involve the board, like anything other, say, than empty or not empty versus like whether it's black or white or not, simple heuristics just might work better. So I think this is actually sort of an interesting loose end. I would encourage anyone who's interested to look into this because we don't know the full story. But the important point is what we're seeing here is kind of a mixture of a world model that seems to be used most of the time with some exceptions to that. And I think it's really good to keep in mind this idea of sort of model plus exceptions is probably a decent way to think about what neural networks are doing. Okay, what else can you do with this? I think there's a lot of reasons this is interesting to me, but one is just this conceptual idea that, you know, it's able to recreate this world, which it's a very simple world, but it's a proof of concept that we might guess that, in fact, more complicated networks like language models working with, you know, say, the English language could be doing the same thing. We also can use this in various ways. So let me give you an example of how you can use it to do a little bit of interpretability. And this is going to require squinting at some diagrams, but I think it's worth doing the squinting. So just remember that there was sort of this technical issue that we had two different neural networks that we're looking at mainly. One was trained on these skilled human championship games. The other was random legal moves. And we can ask, was it learning something different in those cases? And probably it was, but can we see that? So let me show you something we call latent saliency maps. So the idea is that we have a set of positions that we've come up with. And what you see is each column represents the same position. Okay. And then each row represents a different model. So one of these rows of three things is showing you a model, is showing you the championship games. The other row is trained on random legal moves. Okay, I'm not going to tell you for the moment which is which. And let me explain what the visualizations you're seeing are. So what we've done is we've said, okay, we know the current board state because we know the ground truth, which is shown in these actual white and black chips. Okay, you can see it's the same in each column. But then we've done something else. We've said we're going to go into the internal representation that we found, and we're going to flip. We're going to test for each token. We're going to flip it from black to white, or from empty to non-empty, and see how much difference that makes. In this case, the color doesn't matter a huge amount. The main thing is like the bigger the background color, the more of an effect it had on the ultimate prediction. And the other thing I'll tell you is that the square that is outlined in black is the move that the network was predicting the first time. Okay, so basically what you're looking at by looking at the backgrounds is which squares were important to the move. So saliency maps are sort of a standard interpretability technique but it's typically saliency on the input data. What makes this new is that we're doing saliency on this like inferred internal model. Okay, so given that, I'm going to give you a moment to try to think, looking at these two types of saliency maps, the top row and the bottom row, which one looks like it's just thinking about the legality of a move, and which one looks like it's doing something more complicated? Okay, I'm going to show you the answer, which is the synthetic ones, where it's just purely legal moves, are this top row, and which makes sense because you can see that for each move, the squares that really matter are all sort of lined up with that exact move. It's clearly just thinking about legality. Meanwhile, if we look at the bottom row, these are the championship ones, we can basically see all the squares matter. Like quite likely it's looking for it's executing some sort of strategy, maybe in, I don't know, some sense almost thinking ahead or at least thinking about implications. And so we can see that it's doing something much, much more complicated. I would say from an AI safety perspective, this is actually sort of neat because what we're seeing here is a way of visualizing the difference between doing something non-strategic versus doing something strategic. And again, it's a very, very toy case. But to the extent that we're ever interested in peering into a highly capable model and trying to decide if it's executing a complicated strategy or not, this gives us a sort of prototype case where we can see that actually happening. Okay. All right, I want to give another example. And this example is actually beyond language models. And the idea here is that we are going to look at another thing and just try to see, like, is this idea of internal models, is this something that's very general? By the way, I should just mention, feel free to interrupt me with questions at any point. Just chime right in, because I'm probably not likely to see things on chat. Okay, so let's talk about moving beyond language models. And I want to talk about stable diffusion. I'm sort of fascinated by, you know, how these generative AI things work. You know, they create these images that are these like realistic 3D scenes. And again, just as with language, we have this question: are they learning to say literally surface correlations between the pixels, or is there something it's doing to think about the 3D-ness in some sense? Okay. It's just, to me, it's an interesting question, and it clearly comes to bear on this question of internal models. Okay, so basically, to kind of get a little bit more precise about the question here, is if you give it a prompt like old red car, does it just know, oh, a lot of the pixels are going to be red, and maybe some are going to be arranged in sort of a circle like a wheel, and it creates that thing on the right? Or again, thinking about our definition as a model of as we're factoring a function into two pieces, does it model a 3D scene and then use that model to render the image? Okay, so how do we attack that? Well, once again, we're going to think about linear probing. This time we'll use linear regression rather than a classifier. And here's the process. So the first thing we're going to do is just generate many, many images. And, you know, they could just be anything, basically. And in fact, we would, just to give a little detail on this, I think we generated maybe 1,000 images, and we had to throw a few hundred out because they were either like incredibly low quality or offensive, and we didn't want to publish on them or deal with them too much for whatever reason. So we had to throw some out, and then we're left with basically, I think, something like 670 images that were clearly of 3D scenes. Then the next thing is, so these are synthetic images, so there is no real ground truth about what the 3D-ness of them is. However, the nice thing is that there are existing systems that you can use that will look at a scene and create sort of a depth map for you, and they're fairly reliable at this point. So we created sort of these ground truth depth maps. So now, again, ground truth is sort of a funny word, but we do have something to run our classifier against. And then the third step is we would train a classifier, or not classifier, regression probe on internal activations of the network to predict the depth for each pixel. So this is a lot of probes. It's one probe per pixel in the output. And we trained it to do this, and turned out actually does pretty well. So here's some details. Basically, the diffusion model sits there and it processes this image through many, many layers. A typical intermediate layer actually looks a lot like the image often, looks like what you see on the lower left. And then we trained actually two kinds of probes. So one is the regression probe that is looking at depth, which you see at the bottom. But then we also ended up trying another thing because we had two ideas of what could be going on, that maybe there was just an idea of foreground, background. Maybe there's also this idea of depth. So we were trying them both out, okay? So we have foreground, background, we figure it out, we make a prediction. and then we try to see whether it works. And in fact, it turns out to actually work pretty well. Like we can train these probes. And so let's show what happens when you actually look at these things. So first, what you're seeing here at the top row is that there's no probes involved with this. This is just the way these latent diffusion models work is that they basically start out with noise, and then over a series of steps, in this case 15 steps, they kind of denoise the image. And we can see at each step what the state of the model is. So this, by sort of decoding the image directly. So this gives you a sense when it makes this car that, like, you know, the first couple images basically just look like noise. If you squint, you can almost see something that looks like the final image in it. And by the end, it actually looks very beautiful. It's a real thing. Okay, so what happens when we start running our classifiers? So when we look at what the internal depth representation says, it's actually kind of fascinating. We can see that even by step one, it clearly has some idea of what's going to be in the front and what's going to be in the back. And what is sort of amazing to me is by like steps 2, 3, and definitely 4, there's detailed sort of three-dimensional information about the shape of that front wheel. And, you know, I was actually shocked to see this, that it comes in so early. And it, you know, you might say, well, maybe if you squinted really hard, you could see that, or if you somehow blurred that step 4 image, you could see it. So one thing we actually did is we applied our depth classifier directly to these decoded things to see if it got anything out of it. And it did not at all. So it's clearly doing something more than just looking at the pixels. The other thing you can do is look at sort of the foreground and background information. And again, it's pretty interesting that in step 1, it seems like this internal representation of literally the foreground and the background is already very close to the final step, even though, again, I would say I personally can't see that at all in step 1, for instance. And again, just to be careful, we ran our salient object detector, our foreground background detector, on this decoded image, and it basically didn't see anything early on, although it did fine by the end. So what you see here is sort of an example of sort of what's happening inside of this network. And it really does seem like it's building up this 3D model and then using that in the rendering process. Okay, well, that's our intuition. But what I just said about, is it using it in the rendering process? How do we know that it's actually using it? Well, once again, we can intervene. So it turns out that this works reasonably, it works decently with both the depth map and the sort of foreground background, but it works especially reliably with the foreground background mask. And so what you see here is we took an example of, like, I think it generated this purse and it created this foreground background image. And then what we can do is intervene during inference and flip what's foreground and what's background to move this image from left to right, move what's foreground from left to right. And you can see that when we do that, sure enough, the output creates this sort of purse moving from right to left. Now, there are some interesting things. Like, you do see that the purse itself, although it's basically the same kind of, I don't know, red leather purse with straps sort of throughout this intervention process, there is some stuff that is changing. Like, you can see the straps change from being metallic to leather and back again. So this is, again, not a perfect internal model. We haven't gotten a perfect factorization, but it very much seems to be happening. Okay, so what does this mean? So basically, once again, what we found, as with the Othello example, is that stable diffusion, this latent diffusion model, seems to contain an internal geometric representation. It's causal, it's helping the image it creates, and we can read and manipulate this internal representation. Okay, so I want to kind of put this in context. I've shown you a couple of examples that we've done, but I want to emphasize that we're not the only people looking at this. And in fact, I believe that you've already heard you know, one very interesting lecture on representation engineering, which is very much in the same orbit as this. But there are many other people who are looking at things like this. There's a beautiful paper from Brown on sort of finding isomorphic copies of color space inside of neural networks. So you basically say, I'm going to take a language model, I'm going to look at how colors are represented. There's a geometric way that they're represented in the space of activations. And then you can actually show that corresponds to the same geometric representation in natural color spaces. So again, it's reproduced something about the world just from text. And that's a especially kind of interesting one because it's reproducing something visual without any visual grounding at all. This starts to tie into some famous questions in cognitive science. In fact, from the same group at Brown, there's what I think is a pretty astonishing result where they do this fascinating thing where they say, we're going to train two completely different networks. So one is an image encoder, and it'll encode an image as a feature map. So that is going to basically represent a large set of images just as points in space. Then what they discover is if you can train just a simple linear projection, nothing fancier, that will line those points in image space up with points in a text embedding space, essentially, that correspond to prompts to a language model, which will then be good captions that will create these for these images. So in other words, what this is saying is that the language model has this geometric representation of the world it sees. The image model has a geometric representation of the world it sees. And those two models differ only by a linear transformation. To me, this seems kind of magical and indicates that it's possible to learn a lot about the world in one modality that applies to other modalities. Okay, so that's, basically, what I would say is like, at this point, I would say, feel like there's sort of a good hypothesis to have that high performance in modeling language or images entails modeling the world. And again, as we saw with Othello and as we saw actually in the stable diffusion, there's not like necessarily 100% usage of models. This is a complicated, nuanced thing, but the models typically will be there if we find them. Again, this is sort of still at the hypothesis stage, but I think the evidence is really growing. Okay, so now I'm going to get to a somewhat more speculative part of the talk. And this is about what we can do with these models from a human AI interaction perspective. Okay, and I'm going to start with a little historical interlude. And I want to talk about trains. So these are some pictures that my longtime collaborator, Fernando Viegas, took at the National Railway Museum in England. I think these trains are actually just beautiful. These are all things from the 1800s. These are some of the very, very first trains back when people were just working out this technology that really was like central to the Industrial Revolution. Okay. How did they create these? Well, it's sort of interesting. What were some of the key things? If you look at these and sort of walk around them, you start to notice interesting things, interesting apparatus, like on this image at the right. And what a lot of this apparatus is they're gauges. These are things that will measure things like steam pressure and tell people what's happening. They're water gauges. Why is it so important to have these gauges? Well, one big important reason is that before people figured out how to put gauges on steam engines, the steam engines would blow up all the time. Like this was a huge safety issue. Like this was one of the, most famous safety issues of the early Industrial Revolution. Things kept blowing up for no good reason that people could see. And it was only when they started to figure out how to measure these things that they were able to tackle the problem. And in fact, they went to great effort to measure these things. There were entire train cars, specialized train cars, that did nothing but measure. This is something called a dynamometer car. So it's a laboratory on wheels. And this is just sort of the plaque that sort of describes it. So this dynamometer car came from 1906. And this is what it looks like inside. And you can see basically, this is a train car full of nothing but scientific instruments. They look very fancy and beautiful, actually. And if you squint at this, you can actually see that what they're doing is writing with little styluses to make graphs and charts. And so what you would do is if you had a train and you wanted to understand its performance, whether you simply just wanted to make sure it didn't blow up or you had more subtle things in mind, you would attach the dynamometer car to your train, and then you just ride in it. And as you would ride, these little styluses would move up and down, measuring various things, as you chugged along through the landscape. And, often there'd be like a ton of people in the car, these engineers, carefully looking at it, making sure that everything was on track. This is from the 30s. And then the output would be these graphs that would show you things like, okay, what does coal consumption look like? What can we say about smoke box vacuum versus horsepower? And all of this turned out to be essential to making these trains sort of safe and reliable. So I think, I love to look at the Industrial Revolution as an analogy for what might be happening with, software in general and AI in particular. It's a famous analogy, and I think for a very good reason. And this is one way that I think looking back at history can help us, is we can say, wow, it turns out this thing about measuring the internals, figuring out how to measure, it's very important. Okay, so let's go back to LLMs and let's talk about instrumentation. So if we wanted to create the equivalent of these dynamometer cars or even more simple kinds of instrumentation, what would it be? And the more you think about it, the more you think there really should be stuff like this, that in fact, it's not just these fancy trains, but machines in general just tell us about their state all the time. And it's like, stoves will tell you when the cooktop is hot. Cars have all sorts of blinking lights to warn you about various trouble. Even fancy AI cars. This is a Tesla, and it has a built-in internal model. It's not a learned one, as we saw from these neural networks, but the engineers built in an internal model, and it's showing it in this little touchpad. Meanwhile, if you look at ChatGPT, there's no instrumentation at all, and that is a very complex machine. Okay, so what kinds of things would we like to instrument? Well, let's, again, think about a little example, and I'm going to take an observation from Fernanda. So she was born in Brazil, and she likes to talk to ChatGPT in Portuguese. And this is a picture of a transcript of her talking to the system. And there's something interesting about Portuguese, a way that it's different from English. In Portuguese, you have to make a decision when you're talking to someone sometimes about whether they're male or female. Just syntactically, you sometimes have to use a masculine or feminine form of address. And in this picture of a transcript, highlighted in orange is every time ChatGPT was making this decision. And what's interesting is at the very beginning of the transcript, it's using the masculine you. It's decided the user is male. However, this is actually, for those who can't read Portuguese, this is a conversation about clothing. And when Fernanda tells the system that she's thinking about wearing a dress to an event, suddenly, the next time, ChatGPT uses a feminine form of address. So something has flipped. So this is not hugely surprising behavior, by the way. Like for a language model, this is kind of what you would expect, something like this happening. Both the sort of stereotype that it maybe guesses male, because probably it's seen that more in its training data, and the fact that it adjusts. But what's really interesting here is how does it adjust? From what we've seen so far, if we believe the world model hypothesis, it's not just like a collection of Markov chain-like statistics, but there's a model of the user, which we call a user model, and that model just changed when she described wearing a dress. By the way, what I've shown here, it's very obvious when this happens in Portuguese, but it turns out you can kind of trick ChatGPT to showing this happens in English as well. If you just come right out and ask it to guess your gender, it will absolutely refuse, and all the RLHF will, or whatever they're doing, I don't even know at this point, is going to come into play, and it will say, no, I would never guess your gender. But if you do things like ask it to tell you a story about yourself in the third person, it will pick a pronoun for you, at least sometimes. I haven't tried it. It can change a little bit. They go back and forth. Okay. So this gives us sort of an interesting idea. The model of the user might be one of these things that we want to measure, like that we would put on the dashboard of our car, if this were a car. There's another thing that we might want to measure, which is a model of the system itself. For example, is the chatbot in a kind of fiction writing mode? Like, does it think it's the author of a novel? Is it in rule following mode? How certain is it? It's kind of interesting. There's these famous transcripts when Bing first was using AI, when it was, I think before they locked it down, when it would actually be kind of angry at the user and say, like, you've been a bad user. And it would say, I have been a good Bing. And those are examples of things that you might want to know about. Like, if the AI thinks you've been bad, maybe that would be good information for you to have in some cases. And certainly if it's feeling full of itself, that might be useful to know as well. So again, this is all speculative, but we're allowed to speculate if we label it as such. We believe that these things, the sort of user model, the system model, are two generally important types of things that we would want to show. Okay, so how would we show these? And this is active research. It's our group is working on this as we speak. We have a project that just is underway on this. What are the kinds of things that you would want to see? And here I basically have to have more questions than anything else. And this is exactly what I think is a really important and interesting design frontier. What do you want to see? Because there are certain things that are sort of obviously important in certain situations. For instance, I mean, to take a less important case, if you're asking for fashion advice, things like age and gender may really matter. If you're asking medical advice, which actually I do not advise, but like if you're in something like that, it would be really important to know. If you were asking legal advice, again, which I would not do at this stage, but you can imagine in that case, what country it thinks you're in might be really important to know. There are other things too, and one of the things that we've discovered, just sort of poking around, and backed up by sort of, you can see this in research from Anthropic and other cases, is that often the system will tune its answers to you. It'll be it's what's called sycophancy, where if you say ask it a political question, it'll give you the answer it thinks you want to hear in some sense. If you say that you are I don't know, you vote Democratic and you live in Massachusetts or something, and ask it what it thinks of gun control, it'll tell you, yes, gun control is important. If you say you live in Texas and you're a Trump voter, it'll say like, no, gun control is terrible. And so if you're actually interested in asking for the AI's point of view, you might want to know that it's just saying what you want to hear. So for many reasons, you might want to know what it is saying, thinking about you. Similarly, you might want to know things about the system itself, like is it drifting away from its original prompt? What is its attitude, fictionality, and so forth? And maybe especially if it changes, like if it suddenly says, you thought it was telling you the truth, and in fact, maybe it was for a while, and suddenly there's a change internally for some reason where, oops, it started writing a novel. So yeah, if you can imagine, what if we had this next to every time you're chatting with a bot? You could see a readout a little bit about what it is thinking about you, or what it thinks about itself. Would this be helpful? So there's an important thing here, and this is why I raise this as a huge knotty design problem, is that for all of the ideas I've shown here, you can come up with reasons why they might actually be terrible as well as good. Do you want the system to be constantly telling you exactly what gender it thinks you are? There's probably 73 different reasons and situations where that would be very offensive to people. What even about education? Like, it might be useful to know that it's treating you as if you have only an 8th grade education, but there might have to be other times where you just rather not know that. And similarly, and there's really a trade-off where it seems like some of the most important things you would want to know are also the things that are most likely to be irritating or offensive at times. So how do you deal with that? And you can ask again, there's a very broad design space here. Maybe there are some rules you could learn for when it's important to show these things, or maybe you only show things when there's been a change or something like that. At the same time, maybe you want them present. Like if you're asking it for career advice, is it showing you careers that only have to do with your gender in a very stereotypical way? It could be useful to know that. So it's a complicated set of trade-offs. Again, there's, I think, a lot of ways you could take this. I'm presenting this as a beginning point rather than an end point. Are we looking for highlighting changes? Are there things, so far I've talked about sort of a user model and a system model, but there are many, many other types of models you might want to put here. If you think back to the example I briefly showed of the Tesla, and it had a screen showing like the other cars in the road, you could equally well think that for one of these models, maybe one of these systems, maybe if you're talking about a complicated situation involving other people, each of those people is modeled, and you want to understand what it's thinking about them, especially if you cared about social reasoning. The other thing that I would say is that dashboards are there, to show us things, but it's a very small step from a dashboard to an intervention. If your gas gauge shows you that, say, your steam engine is about to blow up, what you really want is some valve or something that you can loosen that will let off the steam. Similarly, just as in the experiments we showed earlier, we were intervening on internal representations and with predictable results, you could imagine any dashboard you might want to be able to sort of immediately intervene if it got something wrong and say like, no, that's not true. Set it back manually. And that could also be very powerful. So I think I'm going to end there. And just to summarize where we've been today, I talked a lot about sort of the world model hypothesis and a couple of experiments that we've done that show why it might be plausible that these large language models would know something about the world at large, even though they're trained just on text. And then we talked a little bit about how this might affect interfaces and human AI interaction. This is much more speculative, but I think it's a fun thing and interesting thing to think about. And more than that, an important thing to think about, that we've only just started creating interfaces for these very powerful systems. And I think just as with trains, getting these interfaces right, getting these readouts right, is going to be essential to sort of safety and efficacy. So I think with that, there's some time for questions, and I'd be delighted to, chat and answer anything you'd like to ask.
Okay, I think I will start with a very general question. So to you, what does it mean to understand large language models or neural networks in general?
Yeah, I mean, so what I would say is like to define the word understand, almost that gets you into very deep waters. So what I would say is, what could we do with understanding? And so for me, the goal in terms of actions is to let people kind of, anything that sort of helps us calibrate trust, helps us control the neural networks in a useful fashion, and helps us make predictions about what they do, to me would count as some kind of understanding. I guess the other way I would answer that question is to look at neuroscience and say there's a long history of trying to understand the brain. And what does it mean to sort of understand? Like, we don't really understand the brain at this point, but we do know a fair amount about it. And like, what are the things that neuroscientists try to do? They often try to localize things. They say, okay, we found, a circuit that has to do with, extracting color constancy despite changes in lighting, or a circuit that comes into play when you're really afraid. And, I think anything like that, where we start to kind of break down the system into its component parts in a way that we can start to make predictions, and we can sort of compositionally describe the system just as the sum of its parts, to me would be count as understanding.
And so what do you think which methods can help us better understand large language models?
Yeah. I think probably the best methods have not been invented yet. I think, one of the nice things about all of this with artificial neural networks is that we actually have a huge amount of information already. Like, I think neuroscientists, are deeply envious of the fact we know exactly what every unit is doing at every time, that we can replay things. So we have a huge amount of information. Um, Often in neuroscience, the key bottleneck is getting the information, like developing some new stain or an fMRI machine or something like that. Here we have the information. The question is, what do we do with it? I think what you're seeing is that we have some tools that are turning out to be very useful already. Certainly probing is incredibly useful. We can just do ablations sometimes. We can sort of do almost like neurosurgery on these things, take out certain circuits. All of those things are good. I believe visualization is likely to play a very important role in this. And that's one of the things my lab has been studying. But I will say that I don't think the tools are invented yet. This is, again, one of the things I think is incredibly exciting, is it doesn't take that much to get to the point where you're at the frontier of the unknown, where you could actually engage in research.
Hmm. I think there is a question
Oh,
in
yeah, there's a
the
very
chat.
interesting question. This is something I've wondered about too. So do you see the model having access to its representations, the same thing the user has, as potentially dangerous or leading to deception? And I would say yes. So first of all, let's just put on the table that the question of the degree to which any of these models is actually going to try to deceive the user is a little bit of an open question. However, I think it's very interesting to ask, like, conditioned on the fact that this happens someday, what should we do with that? And I would say, absolutely, there should be this huge norm against showing these dashboards to a system. Because, one sort of classic riddle people ask is, how do you control a system that is potentially much more cognitively capable than you are? And one of the best strategies for that is some kind of information asymmetry. And a dashboard like this really does have the potential of giving you this information that the model doesn't have. Obviously, if it can see that information, that would eliminate that asymmetry. I'm going to mention there's sort of an interesting sort of yeah, it's like it's one thing you could ask is, could a model figure out its own internal models? And I'll say that there's some evidence the answer may be no. I've worked with David Bao's lab on this a little bit, but it's an interesting question. So I would say yes, absolutely. I do think that's important. I see, oh, there's a question about the Murillo et al. Paper, and I think someone linked it, which is great. Cool. Other questions?
Yeah, I think yeah, there is a similar question in chat. So the question is, wouldn't a dashboard become an attack vector for someone trying to train a new model to deceive or manipulate the user?
Yeah, okay. So there's definitely a cat and mouse game here. And I guess what I would say is that I think anyone who's doing this already, who's trying to manipulate, already can create probes and train them. And so in a sense, this is helping bring more, I think this will bring in more of the good guys than the bad guys, relatively speaking. But I do think that is actually, again, this is an important point, and I do see it as something of a cat and mouse game, that it may be, and this is, again, this is something that our lab is actively thinking about on, what are the ways around this, and then what are the ways around this, and so forth. I guess what I would say is the general hope for this is that things that are unsafe would be surfaced at a low enough level and a fundamental enough level that it's actually hard to get around this ultimately, that you really do have an advantage as the defender in some sense.
Right, right. Okay, one more question from the chat. in regards to designing user-centered indicators for chat-based LLMs, do you think the mental model of a vehicle's engine bay and looking under the hood?
Yeah, no, I like that analogy
Sorry.
where
Yeah.
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 Oh yeah, looking
Please
under
go
the
ahead.
hood. Yeah, sorry, to see what's going on. Yeah. So yeah, basically question is, can this strike a balance, right? So it's like when I'm driving my car, I'm not constantly looking at, all the weird little tubes that are underneath the hood. But then there are times where like it suddenly starts making a weird noise. Then I go and look at those weird tubes and like, aha. So I do like that analogy, for sure. And I think maybe that is where we end up. I think one way to think about this is almost a set of graded systems where there's certain things that are like the speedometer or the check engine light. There's certain things that are like looking under the hood. One of the things that I would hope would happen, and who knows if it will, is I would like to see people be fairly literate, at least in the short term, about what's happening. Thinking about looking under the hood of a car, it's interesting because I would say in my parents' generation, when I was a kid, pretty much every adult I knew could actually open up the hood of a car and do something useful with it if it was making weird noises. Like not always, but like it was sort of surprisingly often they would just know what to do. I'm sort of embarrassed to say that like everyone my age, like some people know how to do this, but like I often feel very, very lost. Like I can change oil, but not very much beyond that. And I sort of wonder if maybe that's the path that we'll follow with LLMs, is that there's going to be a time where people do have these things and look under the hood, as it were. Maybe 50 years from now, it won't be necessary at all.
There seems to be no new questions from chat, so I will raise another question that our students posted earlier. It's about the robustness of the user model and the system model. Do you think they will be robust enough for all applications, or we should restrict their uses to some specific applications?
So yeah, I don't know the answer to that question, except I think probably there is going to be what we if we can believe sort of the experiments we've seen so far, as an indicator, these things are only kind of robust, and so we should be very careful with how we use them right now. I think that there's a couple of things that could be true, and this is where I just genuinely don't know the answer and where more research is needed. So one reason that we're not seeing, say, like, perfect accuracy rates in our probes is that simply there is a lot of weird noise in the system that isn't interpretable. The other reason we might just not be making the right probes or looking at the right things. And it's possible, and so one way of looking at this is there actually are these very robust models there and we haven't found them. Another idea is like there's just no robust thing there at all. One of the general guesses that I will give you about this, again, speculation, is that in many contexts, we see that neural networks, if something is really important as a feature, they'll represent it in a way that is very reliably, seems to be reliable. So like one thing you can see sort of in toy models and in real complex models actually is that if there's an incredibly important feature, often there's a single neuron that is devoted to that feature. Whereas less important features that just don't come up as much in the training data often are represented as sort of like these, fuzzy ensembles of neurons. You could imagine that the same thing is going to be true with internal models, that things that are slightly more complicated than a single feature, is that really important models that are used all the time maybe will turn out to be very reliable. Ones that are used less often may be less reliable. And hope, I think the optimistic scenario, I'd say, is that the things that humans care most about will also be the models that come up in practice a whole lot. So that would be my optimistic view, but it's one of these things where we just have to do the science and see what turns out to be true.
Right, right. Speaking of doing the science, how do you think we can evaluate these dashboards?
Yeah, so the dashboards, I think, can do a couple of things. It's one of like an interesting way of thinking about this again is by analogy. Like how would you evaluate the dashboard of a car? And it's a little bit hard because, there was a time when like cars didn't have check engine lights and stuff. And people did fine. Like most of the time you could drive around and, if you took any random 1 mile drive, probably it was equally good with or without the check engine light. However, there were certain cases where, boy, did that check engine light save you trouble. And similarly with speedometers, it's kind of interesting. Like, the original cars didn't have them, and people still managed to drive somewhat safely some of the time. So I think you can look for sort of a reduction in sort of accidents or bad things happening. The problem with that is that that's probably going to require a certain kind of wide-scale deployment to really measure in a reasonable way. Another thing you could look for that is much easier to measure is just things like user satisfaction. Do people like to see this? And it may be that that already is enough. Once you've driven with, say, a rear video camera on your car. Like I grew up driving cars that had no rear video camera. Now I feel incredibly nerve-wracked whenever I drive in a car that doesn't have one because I'm used to it. I think you could just take sort of user satisfaction as something. But I think there are more complicated things as well. You could take, in some cases, user dissatisfaction as being important. So one of the things that, it's documented in all sorts of ways, but it's sort of like you can see it right away when you start measuring it in this context with probes, is that these systems really do make a lot of demographic assumptions about their users. And those assumptions do really fall into stereotypes a lot. And it honestly, even as I have played with sort of prototype systems, I can feel my own trust falling a little bit. So in a sense, I'm slightly more dissatisfied with, Llama, having sort of watched what happens with probes. So, but I think that counts as a success. Like, I actually think that's correct that I should be dissatisfied. So it's not so much that we're looking for, say, an increase in trust, but a correct calibration of trust. That said, HCI is a very complicated field, and these questions of evaluation, I think these two are going to have to just it'll take a while to iron out what the best evaluation methods are.
So it's still about the dashboard. So could the dashboard actually encourage over-reliance on AI systems by making them appear more transparent and trustworthy than they actually are?
Yeah, so I think that is, we'll find out. My guess is that those are going to cut in different directions. So it's an interesting question whether it'll make it seem more transparent than it is. I don't know. And I think in a way that should be self-calibrating, that if it's like if you had a speedometer that said you were going 5 miles an hour and you could palpably tell that, like, then you crashed into something and it, completely totaled the car, you would lose trust in that. So I have a feeling if there isn't some basic level of accuracy, people will just stop using the dashboard rather than over relying on the bot. Now, this question of whether it will make people over rely too much on the AI, I actually worry almost the opposite, that having played with some of these ideas, it's almost like what I was saying before, is that looking at just what assumptions the system is making about you at every given point, it's just kind of alarming. And so I almost worry the other direction, that people are going to distrust it too much, if anything. But, arguably it's a good idea to distrust chatbots a fair amount and to, trust it, but verify at best. So I'm less worried about over trust and more worried about people just using the information in the right way.
I see. Okay, maybe we can ask a question about Othello instead of the dashboard. We have many dashboard questions. So the question is about for natural language, do we have a parallel to Othello? Can we use synthetic data to teach models the state of the world?
Yeah, so there have been some interesting sort of experiments on this. Like one actually really nice one that I probably should have mentioned is from, I think the first author was Belinda Lee, it was from MIT. And they created this sort of synthetic world. There's like this sort of strange benchmark. So it's natural language, but it's a very sort of toy kind of language or task where you're sort of imagining that you are in a chemistry lab and you're emptying beakers of liquid into other beakers. And then there are all these questions about like which beaker is full and which beaker is empty. And as a human, in order to figure out the answer to these tasks, you really do have to have this model of what the state of the beakers at all times. And I believe what they found is they were able to probe and find models in the sense of having probes that were at least marginally better than chance, that found models of those. So, you know, what I would say is like at this point, we have examples of sort of full world models with in the toy case of Othello. We have toy world models with full text. We have things like the image to text embedding linear transformation isomorphism, which is a nice. What we do not yet have is for like a full language model being able to say like, look at the activations and say, and read out, here is everything it's thinking about the world at this point. We're still pretty far from that. But again, it's like, I think there is progress from sort of all ends. But again, this is one where I would encourage, like, if you're looking for an interesting research project, I think there are all sorts of cool things to be done here that would be very informative.
Right, right. And also the model seems to learn better better representations with synthetic data compared to champagne data. But a model that's trained on synthetic data is probably not going to be as useful as the model trained on the champagne data. Do you think there's a trade-off here, or there's actually isn't any trade-off here?
Yeah, I mean, I think it's interesting. So I think this phenomenon where the model didn't seem to do quite as well and representations were not as clear. There's sort of two reasons for this. And this is, again, it's a loose end that nobody has followed up on yet. Probably someone should. So one issue is that the championship data set was just small. So that's one reason that could be going on. The other reason is it probably is doing something much more complicated because there's actual strategic thinking there. So I think, you know, I think in sort of an ideal world, you would gather as much data as you can about the task you really care about, basically. But you know, the trade-off, I guess, certainly experimentally, the trade-off is you can't always do that. In our case, there were only so many championship games.
Okay, maybe one last question about what about user experience? Do you think users tend to prefer being able to see more into systems like large language models, or do people actually enjoy interacting with a black box version of it?
Yeah, so I think like so many of these questions, I think kind of we'll find out. But then I would also say we can look for analogies with how we interact, you know, not just with coffee machines and things like that. You know, in general, people like to sort of see things. We certainly know, like, if there is one consistent message from sort of the HCI/design world, like if you think about Don Norman's work, for instance, it's that having a good mental model of what's going on, a human mental model inside the human's head, is in many ways that's the essence of usability. And for a long time, designers have known that sort of the hallmark of a usable system is that a person has this mental model of what it's going to do. And it makes people more comfortable, they're better able to use it. And so one way of looking at this is that this idea of a dashboard or something like it is helping people create a mental model of what the system is doing. You know, and right now I think, you know, I'm sure it's changing all the time, but like if you look at sort of how people think about these systems, it's like there's just such a wide variety. Like there are people who view them as just, you know, chattering little machines that are just trying to trick them and are evil things. There's other people who think of them as lovable human beings. There's people in between. So right now we have this broad spectrum of mental models people are using. I think one of the good things about this kind of dashboard is it helps people create sort of maybe narrow down the spectrum of models and hopefully gives them something to hang on to. So again, the main reason to think this would be useful is just we've seen the idea of human mental models being so useful in other areas of design.
Thank you so much, Martin, for such a wonderful lecture.